this lesson, I'm going to teach you how to approximate a number provided in decimal form as a rational number. Now, there are many different ways that you can do this, but in this lesson, I'm going to show you two different techniques because each of them provides you with different insights about rational numbers. The first technique I want to show you is called the Farey Sequence, and it allows you to approximate any decimal value, including a real number, with a mediant. And a mediant is something I'm going to explain in just a moment. Now, if you're going to understand the Farey sequence, you're going to have to understand the mediant first. Now, to help you do that, I've actually drawn on a little bit of a graph over here. This axis over here shows the value of a numerator, and this value shows the value of a denominator. So, for example, if we chose the numerator to be 2 and the denominator to be 5, then this point over here represents the fraction 2 over 5. If you stay on these grid lines over here, then every point where the grid lines meet represents a completely different fraction. So for example, this point over here is 1 on 1, then this point is 2 on 1, and this point over here is 1 on 2, and so on. Now, understanding this diagram is actually really important to help you understand rational numbers. So the first thing I want to point out is that this particular point has a numerator of 1 and a denominator of 2. So this point is obviously 1 on 2. But one of the interesting things about a fraction is that if you double both the numerator and the denominator, then the fraction isn't going to change. So to get to this point, we move to the right by 2, and then we moved up by 1. Well, if we move to the right by 2 more, and then up by 1 more, then we'll have another point that's also equal to 1 on 2. So for this point, we can see that the numerator is 2, and the denominator is 4. So that means the point here is 2 on 4. But as you know, 2 divided by 4 is the exact same thing as 1 divided by 2. So therefore, both of them are equal to 0.5, and both of these points must be the same. Now in fact, if you continued this line all the way down, you would find a whole bunch of other numbers that also equal 1 on 2. So as we can see, 1 on 2, 2 on 4, 3 on 6, 4 on 8, and so on, all have the exact same value of 0.5. So if every value on this line has the exact same value, then in a sense, every single line represents a particular fraction. So to make a comparison, how about we pick another point? Let me pick this point just as a simple example. This point has a value of 4 on 2, and as you know, 4 on 2 is bigger than 0.5. So therefore, everything on the line through 4 on 2 is going to be bigger than everything on the line through 1 on 2. If you think of these two lines like hills, this line over here is steeper, and it also represents a larger value. So we can conclude that larger numbers are represented by steeper lines on this particular diagram. Armed with these two facts, we can actually explain the mediant to you very easily. So let me get rid of everything we don't need, and we'll focus on the medians. So I've gone ahead and actually marked on two particular fractions on this diagram. This one over here we're going to call a over c, because the numerator is a and the denominator is c. You can see that the numerator is just 1 and the denominator is 4, but I want you to imagine it being able to move around to anywhere you like. Similarly, this point over here is b over d because the numerator is b and the denominator is d. The numerator, of course, is the number 5 and the denominator is 2, so this is the point 5 on 2, but again, it can also move around. Now I can finally tell you what the mediant is. To construct the mediant, all we need to do is to add up these two numbers to get the new numerator and to add up these two numbers to get the new denominator. So the new numerator is a plus b and the new denominator is c plus d. Now as you can see, this point is going to land right over here. So this is going to be the mediant. Now, just by taking one quick look at the mediant, I hope you can convince yourself that the slope of the mediant has to be between the slope of these two lines. You can also construct the mediant in another way. I want you to notice that the first fraction moves to the right by c and then up by a. The second fraction moves to the right by d and then up by b. So if you started over here, then moved to the right by d again and then up by b again, you'd be back at the mediant. Or to help visualize this another way, you can imagine taking this whole piece and just moving it to the right so that it's over here. There was nothing special about moving this piece to the right hand side. You also could have taken this bottom piece and moved it up, but in either case you can see that we're going to end up with a parallelogram here. So just to explain this here, if you have a situation where A over C is smaller than B over D, then the median of those two numbers, which is this yellow one over here, is guaranteed to be between the first number and the second number. Now I want you to imagine approximating a number that lies along this line over here. If you have this number over here and this number over here, where one is smaller and one is larger than your target number, then the median is going to give you another number that's going to help you narrow down the range. So this time the range can be this rather than this whole area. If that doesn't totally make sense, let me actually show you this with some explicit examples. I want you to imagine that you were trying to approximate a number that you knew was between the number 0 and the number 1. Keep in mind that 0 over 1 is just 0. Well, if you started by trying to find the medians of 0 over 1 and 1 over 1, you would get a number that's guaranteed to be between them. The medians of these two numbers would just be 0 plus 1 on the top, which is 1, and then 1 plus 1 on the bottom, which is 2. So the number you're after is just 1 over 2. Well, at this point, the number you're after can either be between this range or it can be between this range. It can't really be anywhere else. But then we can just continue taking medians as well. As you take more medians, you're just going to narrow down the range. So for example, the median between these two numbers would be 1 on the top and 3 on the bottom, so the number is 1/3. If you knew that the number was smaller than 1/2 in the previous step, then you've actually narrowed down the range even further. The number can now be between 0 and 1/3, or between 1/3 and 1/2. But then you can also take the median of these two numbers. That'll give you 2 on the top and 3 on the bottom, so the number here would be 2/3. So now that you have these two pairs of medians, the number you're after can be in between this range, this range, this range, or this range. But then again, why stop there? Let's just keep going. We could take the median of these two numbers to get 1 over 4. The median of these two numbers would be 2 over 5, and then these two would be 3 over 5, and so on. So then at this stage, after you take the medians again, we have 1, 2, 3, 4, 5, 6, 7, 8 possible intervals that you could be a part of. In fact, every time we take the medians, we actually increase the number of possible intervals by 2. So therefore, repeatedly applying the medians over and over again can get you to a smaller and smaller interval. Now, a method like this is really cool and everything, but until you see it actually applied, it won't really make much sense. So let's go ahead and do an example together to see how you can use this. Okay, so I'd like to estimate the square root of 3 as a rational number, given this decimal approximation, 1.732050808. In the lesson where I actually introduced surds, I showed you how you can actually generate these digits. But what we want is a rational approximation to this square root of 3. To make this problem easier, I'm going to break this number into an integer part and a rational part. So I'm going to keep the 1, but then I'm going to keep all the decimal parts separate. So I'll rewrite this as 1 plus 0.73 and so on. So by doing this, I'm only going to try estimating this part over here. And I know that I'm just going to add 1 to it at the end. Now, the way we start this is we start with the numbers 0 over 1 and 1 over 1. So let me put them down first. Now, I've written this almost like a coordinate, where the first number represents the minimum and the second number represents the maximum. We know that this number over here is going to be between the number 0 and the number 1. And the first step is going to be to find their medians. The median is, of course, 1 over 2. And I want you to realize that 1 over 2 is the exact same thing as 0.5. Now, the number we're trying to approximate is 0.73, and 0.5 is smaller than 0.73. So we should replace the old minimum for 0.5, or 1 over 2. To show that the minimum changed, I just drew it in a different color. Now at this point, I want to find the medians again. So I'm going to add the tops, and if I do that, I'll get 1 plus 1, which is 2. And then I add the bottoms, so I get 2 plus 1, which is 3. Now, you may or may not know this, but 2/3 is approximately equal to 0.6666 and so on. Now, of course, 0.6 is still smaller than 0.73. So that means we need to replace the minimum one more time. So instead of it being 1 on 2, it's now going to be 2 on 3. So now we've actually narrowed down the range even further. We know that this number over here is going to be between 2/3 and the number 1. But why should we stop here if we can just keep going? So if we do keep going, we find the median one more time. If we add the tops, we're going to get the number 3. And if we add the bottoms, we're going to get the number 4. So the next number we're after is 3/4, or 3/4. And I hope you know that 3/4 is the same thing as 0.75. Now, just in case you didn't know that 3/4 was 0.75, you could always just type 3/4 directly into a calculator. But this time, 0.75 is actually bigger than 0.73. So therefore, we're actually going to replace the maximum rather than the minimum this time. Now at this point, I've narrowed down the range even further. I want you to realize that 0.73 and so on is somewhere between 2/3 and 3/4. But is anything really stopping us from just continuing this process forever? Well, not really. You could continue this process for as long as you liked, and the longer you kept going, the closer you'd get to this actual value. However, you do need to be a little bit careful, because if you just kept going forever, the numbers you're approximating with will get very, very close to the number you're trying to actually approximate. And that just makes it a little bit hard to know which one's actually smaller or larger in that case. Now, this is a really useful method because of how simple it is. You just add the tops and then add the bottoms, and then you end up with another number called the median, and you can just use it to replace either the minimum or the maximum. And the longer you keep going, the closer you'll get to the actual value you're trying to approximate. Now in this case, we can see that this number is closest to 3/4. That's the closest number we've gotten so far. So we can say that root 3 is approximately equal to 1 plus 3/4. But of course, this method does have one really big drawback, and that's the fact that it is really, really slow. You could keep doing this for a really long time, and it would take you a very, very long time to get a useful approximation to a number like the square root of 3. But this method is also quite useful because it can be used to give you an ordered list of rational numbers, and that's useful in itself. So just leaving you with this method wouldn't really be very good, would it? So I'm going to show you another method that ends up being a lot faster, and it's also a fair bit easier to explain. So this new method is called the continued fraction method, and it approximates numbers with an infinite sequence of nested fractions. Now that seems like a really complicated definition, but let me actually show you one, and you'll see that it's not really that hard. Now there's this number known as phi, that you'll learn all about as you continue learning mathematics, but it is approximately equal to 1.618033988 and so on. Well, this number phi can also be written as a continued fraction in this form. If you write 1 over 1 plus 1 over 1 plus 1 over 1 plus 1 over 1 and you continue doing that forever, you'll get closer and closer and closer to the value of phi. So I suppose the only thing I have to show you is how we know that these numbers are all supposed to be 1s. But I'll show you that in an example in just a moment. But one thing I also want to show you is that you can just stop doing this anytime you like to get an approximation for the value of phi. So for example, let me write one out. Now this over here would be a reasonably good approximation to the value of phi. To show you this, let's think about it. This number at the bottom is equal to 1, and that means this is all equal to 2, and that means this is all equal to 1/2. Then 1 plus 1/2 is 3/4. Now just to make a quick correction here, I want you to realize that we've gone 1 plus 1 plus 1 plus everywhere. We also needed a 1 plus over here. You can see this because the approximation we currently have is 2/3, and that's 0.66, so that means we're missing this 1. But at this point, we can see that our approximation is 1 plus 2/3, And 1 plus 2/3 is already a really good approximation of this value. We have 1.666 as our approximation, rather than 1.618. But if we were to continue this, we would get closer and closer. Now, to show you this, I'm going to give you another example, and we can work through it together. So this time, we want to estimate the number pi, which is also a number that you're going to see very frequently as you study more mathematics. But pi is approximately equal to 3.141592654. Now, unlike the last case, where the first digit was going to be 1, this first digit is 3. So we're going to start off with the number 3 plus 1 on the rest of the continued fraction. Instead of writing the whole continued fraction, I'm just going to label it as the number a. So all we really need to do is to solve this equation for the value of a. Now, to do this, I'm going to start by actually writing 1 on a as a to the power of -1, or the reciprocal of a. Now, writing a as a reciprocal like this is always going to make the algebra a lot easier. The other thing I can also do is I can also swap the left and right hand side of the equal sign, because it doesn't matter where we put things, because they're equal after all. And now the next thing to do is we're going to move this 3 over to the other side, where it will pick up a minus sign. Now the inverse operation of the reciprocal is just the reciprocal. So that means I can just move the whole reciprocal to the other side of the equation, and that will help me solve for the value of a. Now, you could calculate this by hand if you wanted to, but that's what calculators are for, so let's just use the calculator. Now at this point, we know that this value a over here is approximately equal to 7.062513. Now, we could stop here and just say a is approximately 7 and leave it at that. We can even simplify the fraction on the right hand side by multiplying this to get 21, then adding 1 to get 22 all over the number 7. Now 22 over 7 is actually a really famous approximation for this number pi. And in fact, before calculators, people would actually use this rational number as a fill-in for the number pi. To show you why, let me actually type it into the calculator. Rather than having 3.14159, we have 3.1428. It's not exactly right, but it's a pretty close approximation. But of course, as you probably guessed, we could just continue this process to get an even closer approximation. We know that a is the same thing as 7.062513, or at least approximately so. But we also know that a belongs over here. So how about I actually replace it? But then, instead of writing this as 7.062513, we could again just rewrite this as 7 plus 1 on b, just like we did over here. But there is actually a shortcut to finding the value of b that I should tell you about. I want you to realize that pi minus 3 is the same thing as the decimal part of this original number. So technically, all you really need to do is to take the decimal part and then take its reciprocal to find the value of a. Let me actually show this to you with a calculator. So notice that the value we got this time was exactly the same as the value we got last time. So this suggests a really easy way to get the next digit. This value at the bottom is the same thing as 7.062513, and therefore 1 on b is the same thing as 0.062513. Now let me rewrite 1 on b with a reciprocal again. And then at this point, I'll just move the reciprocal to the other side. Now if we plug this whole value into our calculator, we'll get the next value to include in the continued fraction. So therefore, the value of b is going to be 15.99667 and so on. So our best approximation for b is going to be 15. Now we can simplify the fraction at the bottom, and then we can simplify the whole fraction all the way to the top. But instead, I'm just going to plug it into the calculator to give you the answer. So we can see this time that the approximation is even better. This time we have an approximation of 3.1415094. That's correct all the way up to here, and then it starts to go wrong after this point. But we can also ask the calculator to convert this into a fraction as well. So if we were to simplify this fraction, then to simplify this whole fraction, we would get 333 over 106. Now our first approximation was 22 over 7, and this approximation is 333 over 106. Nothing really stops us from continuing this. We could go ahead and add another 1 on C at the bottom there, and we could continue as long as we like. Now we could continue this process for as long as we like. I hope you can see that we can approximate pi, or really any number you like, by following this procedure, and just continuing for as long as we like. The longer we keep going, the closer we get to the exact answer. But I think that just about completes the examples I wanted to show you. So let's just summarize this lesson. In this lesson, we showed you two different ways that you could approximate a decimal sequence with a rational number. The first method was the Farey sequence. The Farey sequence hinges on the fact that if you have two different numbers, the median of those two numbers is guaranteed to be between the other two numbers. If this is the case, you can always close down the interval to get as close as you like to any number that you're interested in. Despite the fact that the Farey sequence was really cool, and it gives you an ordered list of rational numbers, it was really slow to actually approximate any numbers. So as an alternative, we introduced this idea of a continued fraction. The continued fraction allowed you to write any number like this one as a continued set of fractions, like this. The fractions could technically go on forever. The whole idea was that you could just continue these fractions for as long as you wanted to get closer and closer to the actual value. So the whole idea was that you could just stop anywhere you liked to get a nice approximation to your value. Both of these methods are actually really useful methods, and they can both be used to approximate a rational number. Even if you ask your calculator to approximate a rational number, chances are it's either going to use this method or this method to actually do that. But at this point, I think I've said everything that I wanted to say about the rational approximations to real numbers. So that just about completes our lesson on rational approximations. Thanks for watching another Trina video. If you want to say thanks, you got to show your friends. Or maybe you should just visit us at trina.org, where you can track your progress and have access to questions and heaps of other awesome stuff. Or maybe you should just like and subscribe. That works too. But either way, I'll see you next time.